our presentation. Uh, let me just introduce our team here today. So we have two presenters here today. There's me, I'm Cleon, and I have my co-host here, Vinod.
Hello.
Yeah, so we are the representatives of our project team today who will be conducting this workshop. But we do have three other members of the team. We have Xuanjin, who is our tech lead for the project. We have Dhruv and Wenhui, who are our other two members for the project. So yeah, the five of us, we have been working on this project for the past semester and really get to share it with you today. All right, so this is what we'll be covering for today's workshop. We'll have quite a few content to cover. So we'll first discuss a bit on explainable AI, as well as its motivations, like what is XAI and why is it important. Then we'll move on to some frameworks that we use for the role-wise analysis of our data. So we use three frameworks here. We use Lime, SHAP, as well as iBreakdown. Then we move on to some comparison of these three frameworks, some limitations of it, as well as its use cases. And finally, we'll wrap things up with some column-wise analysis on our data. And we have used partial dependence plots, or PDP for short, for this segment. So let's start off with explainable AI, or XAI. What is the field of explainable AI all about? Well, in machine learning, many models are trained and used as black boxes, meaning that the user is unaware of the model's internal decision-making processes. Explainable AI hopes to uncover what goes on inside these black boxes. But why do we want to know what's inside the black box, right? Why not just place our full trust in the models we train and use them as they are? Well, I explained the motivations behind explainable AI with a short story. Now, there's a group of researchers that wanted to build a classifier that could distinguish between huskies and wolves. They trained their model and it achieved very high accuracy, right, like 80-90% accuracy. However, they found that there was just one image that was classified incorrectly. So there's just one issue, and it was this image right here on the screen. This image was actually a husky, but it was classified as a wolf by their model. So these researchers, they wanted to find out why this was the case, and they tried to explain the model using an interpretability framework, which is a Lime that we'll discuss later on. And what they found was this: the model was in fact not looking at the breed of the dog, but the color of the background. It turns out that the images of the wolves that were used to train the model tend to have like white or snowy backgrounds. So the model learned to associate light backgrounds with a prediction for wolves. This is, however, an incorrect decision process, and it does not generalize well to all images of wolves. Right? So not all images of wolves necessarily have light backgrounds, but that is what the model learned by itself. Right, so these are some of the other motivations behind why we are studying explainable AI and why it's so important. Well, as you see before in the previous slide, having high accuracy does not necessarily mean that the model is good or making the right decisions. So if you have a black box model that has high accuracy, it may sort of induce a false sense of comfort in your model, and you may think that, oh, it is working well and good, but actually it is making all the wrong decisions under the hood. And secondly, we also want some transparency for our models. We want to see how it explicitly see how it works under the hood, and especially for the more complex models and their outputs. And last but definitely not least, is really important, especially in the field of when you're dealing with regulatory agencies and stakeholders. Because usually when these regulatory agencies or stakeholders are involved, such as like governments, they usually want to know the reasons behind the recommendations that your model is making. Right? These high-level decisions by the complex and opaque models cannot be easily justified, which may sort of put your entire project proposal in jeopardy if the explanations behind certain model decisions are not satisfactory to them. That's why it's always important to not only have a good, well-performing model, but also have an explainable model. And that is the whole reason why we are studying explainable AI. Right, so there are a few categories of explainable AI. We first have interpretable models, which are basically very simple models. So these are models such as like linear regression models, logistic regression models, and decision trees. So these models are considered really simple because they only require a few parameters in constructing the model. and thereby it is very explainable. You can just explain it within a few parameters. We also have some multi-layered interpretability. This is quite a unique case where you take an original black box model and you change the class labels on it by to the labels that they actually predict on the original data set. So using these sort of modified data set, you retrain the model, and that model becomes more explainable because it's trained on the original model's outputs. And thirdly, we have the model agnostic interpretability frameworks, which is actually what we are going to discuss today. So we'll explore these model agnostic interpretability frameworks, the three of which I mentioned just now, which are Lime, SHAP, and I break down in today's workshop in greater detail. Oh, but first, let me introduce what we use for our data set. Okay, so just to put things in context, we use a Polish bankruptcy data set, which you can actually find on the link on the screen here. And what this data set contains is rows of data, and each row represents a company. So like you see ID1, ID2, ID3, so these are like different companies. And the attributes they have are their financial metrics. So for example, attribute 1 here is net profit over total assets. Attribute 2 is total liabilities over total assets, and so on. And there are a total of 64 attributes for each company. And of course, since this is a classification problem, we do have class labels. And 0 indicates that the company did not go bankrupt, so it's non-bankrupt. Whereas 1 indicates that the company, in fact, did go bankrupt. Right, so we have these data set. There are 7,000 plus rows, as you will see later. And each of these 7,000 plus companies have 64 attributes as well as a class label, whether it went bankrupt or it didn't go bankrupt. So to see this clearer, I'll show you some of the code that we did in this project. Right, so it is in the form of a Python notebook that Vinod can share in the chat so that you guys can also take a look at it. Yeah, feel free to run the code alongside, but please do make a copy of it. Yeah, and run it if you wish to. Otherwise, you can just look at the screen, and I'll run you through our code base here. All right, first we installed some libraries that we needed for the analysis. So these are just simple like installations and the regular like imports that you would have in a Python notebook. Yeah, and these are the column mappings, which are just the attributes that you've seen in the slide just now. So like same attribute 1 equals to net profit over total assets, and so on. So here we imported our data, and this is the actual data set that we use. So there are a total of 7027 rows, and then 66 columns, because there's the ID column here, plus 64 attributes, plus a class label. All right, so we just did some basic pre-processing on our data. Yeah, we handle all the NaN values, the missing values, and then we decided to drop a few features as we found that they weren't really contributing much to the explanations that we found later on. And as with any machine learning project, we need to split our data set into train and test sets. We just chose a test size of 0.2, which indicates our training set was 80% of our data set, and the remaining 20% was left for the test set. And we chose to use the XGBoost model here. XGBoost is a sort of a decision tree-like model. So it stacks the multiple decision trees on top of each other to improve on each iteration. And yeah, we found that this model actually helped us achieve a rather high accuracy for this specific data set. All right, so we trained the model using XGBoost. It's just a few lines of code here, XGBoost classifier, and we predicted it to evaluate our model and see how it performs. And we found out it really has quite a high accuracy here, 89.97, so really close to 90% accuracy. Yeah, so that is a really high accuracy score for our data set. And we also did some like evaluations on the predictions, so we can identify the true positives, true negatives, false positives, and false negatives here. All right, so these are the main like data pre-processing steps, and in training our model, the fun part begins when we try to interpret our model. All right, so this is actually the crux of our project. The main bulk of our project is not really in training the model, but in trying to interpret it, trying to explain what's going on behind the scenes. Your black box models sort of classification. All right, so for example, our black box model might have the red classified as a positive, that means bankrupt companies, and the blue region classified as negative, which also means non-bankrupt companies. And the purple squiggly line that you see on the screen is the original model's very complex decision function. So you see, it cannot be explained simply because it's just so complex. There's no sort of formula that you can use. There's no mathematical formula you can use, or rather, no simple mathematical formula that you can use to represent the purple squiggly line. However, if you just want to know one company or like one row of the data set, then it's equivalent to just one single point in your data set, and we call that the instance of interest. Right. So if you see the red cross on the screen, that is our instance of interest. Right. So we just choose an arbitrary one, and we just want the explanations to be around that single instance. We just want to know why that company is getting this certain prediction, right? Yeah. So if you just want to know about that single instance of interest, we can define a local area around that instance of interest. So you see the surrounding like red and blue points around that big red cross. Yeah, that's a part of our local area. So if you just focus on that local area, you can sort of construct a linear decision boundary. Yeah, just the dashed line that you see on the screen. Yeah, that is a learned explanation by Lime that is locally but not globally faithful. What that means is that if you just focus on that area, that local area around the red cross, or it seems to fit the model quite well. So it's just a single line that sort of lies along the purple squiggly line only around that area. But outside of that area, it does not conform to the complex decision function at all. Right? So this means that it's locally faithful, but you can't generalize it. So it's not globally faithful. And that is essentially how Lime works to explain single instances. Because it doesn't really care about the other instances that you're not interested in. So only when you select an instance or a company that you're interested in, it can explain what's going on for that company. Yeah, so Lime stands for local interpretable model agnostic explanations. And it is able to approximate any black box model to a simple linear but explainable model, as explained just now. And how it works under the hood is that it samples instances around the instance of interest. So you select, for our case, we selected one company that we are interested in to explain, and then it samples instances around that company. And it changes the input slightly, followed by testing the changes in the resulting predictions using the original model. So our original model is the XGBoost model that you saw. So what it does, it changes the inputs of our model very slightly. It feeds it back into the XGBoost model and see what the XGBoost model spits out. So and using that difference in the resulting output, it can redraw a linear decision boundary from the original model. So higher weights are assigned to the points that are closer to the instance of interest, and correspondingly lower weights are assigned to the points that are further away from our instance of interest. And this diagram sufficiently encapsulates what's going on for Lime. So yeah, as I explained just now, we have a global sort of very complex decision function that is applicable globally, and we reduce that down to a very simple linear decision boundary that is only applicable locally. All right, so before that, I'll go through the code again for the line part. Yeah, in fact, if you look at our code base, it's actually really simple. Like there's only a few lines of code for each section. So the frameworks that we have used are actually very easy to use, and you can apply them to any data set that you want. All right, so all we need to do for our data set is create a Lime tabular explainer. So tabular, since our data set is in the form of a tabular data set, so we have to use a tabular explainer. All right, and for this, when we just feed in the X-train line, which is our training set, it can sort of learn the explanations for our model. Yes, and so in just 3 lines of code, we create the explainer, and then we show the explainer in this notebook here. And these plots is what we get from Lime. Now, I just copy this onto the slides here to explain it in greater detail. So what we see here first, we must notice that the original model's prediction is shown here. The XGBoost prediction is 1. That means this specific company, if you see, we just selected a single company here. Okay, X test Lime 61. That means it's the 61st index of our test set. It's just an arbitrary number. You can choose any other row. We just chose that row for example. All right. So for this row 61, the original model predicted a 94% probability that this company went bankrupt. Right. So that's why there's a class label of 1 there, having a very high, very large orange bar of 0.94. And the orange bars correspond to the positive correlation to company bankruptcy, whereas the negative correlation to company bankruptcy is represented by a blue color. And the more interesting part is the center plot right here, which is the crux of what Lime does and what Lime is able to give us. All right, so the blue areas, the blue bars that you see here, are the attributes that Lime thinks contributed negatively. So these 3 attributes, or the financial metrics behind those attributes, made the company less likely to go bankrupt. Whereas the orange attributes here are the attributes that lean the company towards going bankrupt. That is what Lime sort of gave us, right? It sort of figured out that this was the case between these attributes. And just as a further example, this we can see the attribute 56 having less than or equals to 0.02. So the original value, whatever value from the data set, if that attribute 56 value was less than or equals to 0.02, it had a positive, it contributed positively to company bankruptcy. So it made the company more likely to go bankrupt. And correspondingly for attribute 5, if it was greater than 37.97 in the original data set, that means the company was less likely to go bankrupt. Yeah, so what Lime can do is give us this really powerful chart right here that just shows us what is going on inside the original model, right? So you can sort of see one layer deeper into the model. Right, so it may seem like all fine and dandy, all well, right? But there are in fact some limitations of Lime. Lime is only able to provide explanations for selected instances of our data set, like the local area that I mentioned just now, right? The instance of interest. It's unable to deduce a more general trend from all your data points. So if you wanted like a general trend from every single company, whether like in general, will companies go bankrupt when they have certain attributes, then Lime is unable to do that, unfortunately. So essentially, it trades off the original model's versatility for a lower complexity. Right, this trade-off is good if you want to explain only single instances, because those single instances will be less complex, so it's easier to explain. However, it's not as versatile as the original model, which can sort of predict the outputs for a wide range of companies. Right, this is only focusing on a single company. All right, so there are in fact other libraries that we can use that takes into account the that actually is able to give you a wider, like broader view of things. All right, so you can take into account all the companies and not just focus on one company. And one library to do that is called SHAP, SHAP. But to understand what SHAP is, we must first understand Shapley values, which is the concept behind how SHAP works. Right, Shapley values is a concept from game theory, cooperative game theory to be specific. Right? In the context of game theory, Shapley values tries to solve the problem of fairly distributing the payout of a game amongst its members or its players. It does this by considering all the different subsets of players and finding the additional payout with and without a player. Right, so this is like a small little game theory or math lesson. So to illustrate this, we can look at the diagram on the screen, which illustrates the game of 3 people. So we have person A, B, and C with a certain amount of payout. And if we wanted to know what portion of the overall payout could be attributed to player A, we will consider all subsets with and without player A to see how much the payout increases or decreases when we include player A. And for instance, we can see that a subset of player A and B earns $7, as shown in this red box here, while a subset with only player B earns $4. So including player A in this case caused an increase of $3. We will then repeat this across all the possible subsets, all the possible like permutations and combinations. And we take a weighted average to find the contribution that can be attributed to player A. Well, the interesting thing about Shapley values is that it turns out to be a unique solution to the problem to distributing the payout amongst the players of a game, if we desire certain properties, or as they are officially known, axioms. So I'll go through these axioms to understand why Shapley values work in theory. The first axiom of Shapley values is efficiency. So this effectively means that the sum of the individual Shapley values of each player is equal to the Shapley value of the whole correlation. So assuming that the dollar values are the Shapley values, so the Shapley values of A, B, and C, versus A, B, and C should add up to 19. Right? So there should not be like external factors if you only consider this world or this scope of persons A, B, and C playing this game. And the next axiom we have, or the next property, is symmetry. This means, mathematically speaking, if we have two players I and J that are interchangeable in any game, then their contributions are equal. So this also implies that interchangeable players or agents should receive the same payout, also known as the same Shapley value. And just to illustrate with the same example on the screen, you have persons A and B that has a combined output of $7, and persons A and C having a combined output of $7. So you see, if you interchange person B with person C, you end up with the same output, right? So the Shapley value of persons B and C should theoretically be equal. So that is what this property is trying to say, symmetry. The next property is the property of dummy players. Okay, again, if a person is a dummy player, or if a player is a dummy player, then the amount that that player contributes to any correlation is 0. So essentially, if you see the example on screen, if there's person A having output of $7, you add person B in, it's still $7. That means person B did no meaningful work, or no output in this case. So the person B is known as a dummy player. And dummy players in this case should receive no payout, right? Because they don't contribute meaningfully to the overall equation. And thus their Shapley value should be 0. And the last property of Shapley values is additivity. Now this just states that if you can separate a game into two parts, then the overall Shapley value for a single player is the sum of the Shapley values for that same player in each of the two parts. So for this example, we assume that in the whole universe, there are only 2 games played that person A is in. All right, so there's game 1 and game 2. And the overall Shapley value for person A is the Shapley value of person A in game 1 and the Shapley value of person A in game 2 added together. Yeah, so it just sums up all the possible situations that person A should be in or would actually end up in. All right, so you may be wondering, how can we utilize this game theory concept, right? It's very abstract, right? How do you utilize this in the concept of machine learning? Well, in the concept of machine learning, the game that we are playing is the machine learning model, and the payout is the model's prediction. While we have the players of the game being the features, the attributes that you saw, our attributes 1 all the way to 64, those are the players, right? So we try to allocate the difference between the model's prediction and the baseline. So essentially, what the model predicts, we are trying to attribute that to all the 64 attributes, like how much did each individual attribute contribute to the overall prediction. So that's the main question we're trying to solve. Right, and let's just look at a simple explanation to understand this using SHAP. All right, so I'll go to the SHAP code that is below. Yeah, so here you can see that it's similar to Lime. Okay, there's only 2 lines or like 4 lines of code if you include like these plotting ones. So it's really simple. In just a few lines, you can explain what's going on behind the model. Here we just created a tree explainer because we are using XGBoost, which is a decision tree based model. Pass our original model, this XGBoost model, into this explainer, and then generate the SHAP values. Just call explainer on our test set. And there we have it. We just generated Shapley values. So we do, again, to focus on the same example just now, we use row 61 of the test set, and we get this plot right here on the screen. Right, so I'll just copy this back to the slides, and you can see that this is an example of an instance level explanation that is generated by SHAP, which means that it attempts to explain the prediction made by a single sample of our data. And for this sample, the model predicted that the company would go bankrupt, right? It has a class label of 1. And I explained before, the SHAP assigns feature attribution values, which are also known as Shapley values, to each feature so that we understand how much and in what direction each feature influences the final prediction. In this case, almost all the features are in red. That means it contributes positively to bankruptcy. While there are two main blue features, attribute 5 and attribute 46, that contributed negatively towards bankruptcy. So when this company had attribute 5 and 46, it's less likely to go bankrupt. And we can also see that the value of attribute 33 is the most significant in influencing the model positively for this specific company. It has the largest red bar, in other words. Now, Lime could do something like this, right? So in the previous section when I discussed about Lime, yeah, it could do something like this. So why are we using SHAP? Well, the benefit of using SHAP is that it can produce instance level explanations, but we can also aggregate all these individual companies together to get a higher level understanding of our model. And for example, SHAP can be used as a way of ranking the features in terms of importance. This is done by plotting the Shapley value of each feature for each sample in our dataset, and then ranking them based on their average Shapley value. So you can interpret the Shapley value as the importance in influencing the overall prediction, right? So for example, this case, we have attribute 24, which is ranked first. That means on average, attribute 24 had the highest, absolute highest Shapley value amongst all the data, when you aggregate all the data points. And this plot, you can use this plot to get an idea on how the distribution of values for any particular feature can affect the model's predictions. And if you see attribute 24, you can notice that the high values of attribute 24, because if you look at the scale bar on the right here, high values are in red and low values are in blue. So the high values for attribute 24 correspond to the red points. And the Shapley values for these points will be negative. You can see that the red points lie further to the left, which is negative values for Shapley value. And on the other hand, the low values for attribute 24, the raw data that we have, the low values are on the right side of this spectrum. So the low values or the blue points, its Shapley value will be positive in influencing the model towards bankruptcy. All right, so there are also some limitations of SHAP. All right, it's not all well and good. In general, SHAP considers all possible subsets to calculate the Shapley values, which is exponential in the number of features and can be very, very computationally expensive. Right? However, in practice, there exists different implementations of SHAP that can be used based on the type of machine learning model. For example, there's tree SHAP, which is a very fast implementation that is able to calculate the exact SHAP values based on for tree-based models. Well, we have deep SHAP for neural networks and kernel SHAP for model agnostic models. Like you can use it for any models, but those are slower and they calculate only approximate Shapley values. Another thing to note is that the models do not accept subsets of feature vectors as inputs. As explained earlier for the computation of Shapley values, so that we need some way to simulate the presence or absence of features. And in practice, absent features are randomly sampled from a background data set, such as the training set that we use. And lastly, the Shapley values assume that the features are independent. So they assume that the attributes 1 all the way to 64 just now, they are not related to each other, which may not be the case. That they may be, in fact, some repeated financial metrics within the attributes that are hidden from us. So in order to consider interactions between features, we can use other libraries, such as iBreakdown that Vinod will explain from here.
Thank you, Cleon. Are you able to see these slides now? Cleon?
Yeah, can.
Clear? Okay. All right. So now we come to the last row-wise analysis library, which is known as iBreakdown. So iBreakdown is actually based off this method known as breakdown. In breakdown, we don't use any surrogate models. And in the contributions of each feature is actually calculated sequentially using a single series of nested conditioning. So this is actually slightly different from SHAP, which actually averages out all your possible conditioning. And studies have also shown that the breakdown is able to produce explanations that are very closely related to SHAP, but in a much shorter time. And the I in iBreakdown actually stands for interaction. Okay, here's the more important part. So many of the approaches we talked about earlier, like Lime and SHAP, these are what we call additive models, which means they omit and don't take into account the interactions between features. This is actually a slightly big issue because the complex machine learning models we build, like deep learning models, for instance, usually have interactions between the features. So when you simplify the explanations using linear models, it means that we will get a less accurate depiction of the underlying model. So I breakdown helps to solve this problem by trying to capture the interactions for instance level explanations, and then it generates what we call non-additive explanations. Okay, so this is how I breakdown actually evaluates its features. So it actually computes the contribution of both features together, and then it subtracts from it the additive contribution of each individual feature. So in our case, it means that it will subtract from the sum of an apple and a banana. From the sum of an apple and banana, the contribution of each individual banana and apple. So it means that basically from 100, you minus 40, minus 45, and you're left at 15. So 15 will be the interaction effect of having a banana together with an apple. So let me take you through some of the plots on the Google Colab itself and help you understand this a bit better. So iBreakdown as well is also quite a simple library to use. What you need to do first is to build an explainer from the DLX library. And what you'll pass to it will be the XGBoost model that you built or any other machine learning model that you built, as well as the rows that you wish to explain. In our case, you'll be explaining the X test and the Y test, so we'll pass that in. If you're interested in explaining the X train and Y train, for instance, basically your training data, you can pass that in as well. The next plot that you see over here, this is what we call the variable importance plot. So this is actually very similar to the B-swarm plot that you saw earlier. And it's also very similar to, for those of you who are familiar with XGBoost, its own inbuilt feature importance plot itself. These two are actually quite similar to what you see over here. The third plot that we have over here, or rather it's actually the second plot, is what we call the breakdown plot. This one does not have any interaction. So this is in a way quite similar to SHAP as well as what you saw in Lime earlier. The interesting one would be the plot after this. This is the plot that takes into account the interaction effect between two or more variables. So I'll go over to these slides and I'll show you how to interpret these plots. So the gray dotted line that you see over here, it indicates the average prediction across all your companies. The dark blue bar that you see at the bottom, this indicates the difference between XGBoost prediction for that one company as well as average prediction across all companies. So in our case, in this plot, it basically means that the company has an increase in probability towards bankruptcy by 0.273. The green bar actually indicates variables or features that have a positive effect towards bankruptcy on the prediction. In other words, they increase the probability of bankruptcy, while the red bar has the opposite effect, a negative effect towards bankruptcy. So on the y-axis, the values of each attributes for the particular company are stated. So when you look at the first row, attribute 48 and attribute 24, when they are taken together, they actually increase the average prediction probability by 0.026. And this is an increase from the average prediction for all companies. In the second row, what you notice is that attribute 13 decreases the probability of bankruptcy by 0.035. So as you can tell, that it's not necessary for there to be always an interaction effect between two or more variables. Some variables can exist independently and can be used independently and interpreted independently by the plots itself. And in the third row, you see that attribute 46 as well as attribute number 5, when they are taken together, they actually decrease the average prediction probability by 0.02. So this is how you would generally interpret I breakdown plot. So now you'll actually compare the three frameworks that we talked about. So this will be the third step of our entire presentation for today. So what Lime does is that it builds a surrogate model, while SHAP uses what we call Shapley values, and I breakdown uses a greedy nested conditioning. So in terms of the explanation, Lime, it actually predicts locally within the vicinity of its predicted values, whereas SHAP tries to fairly distribute its contributions across all the different features or all different columns. And for I breakdown, it's slightly different. It considers the interaction effect between two or more predictors. In terms of time taken, Lime would be the fastest, followed by I breakdown, and SHAP would be the slowest of all three. So all this is just a theory. So how would you decide which framework to use, whether you want to use Lime, SHAP, or I breakdown? So we have a very a very simple decision tree that we hope can help you decide which of these libraries you should be using. So if you suspect that your particular data set has a high degree of interaction between the columns, you suspect it has a high degree of interaction either because of your domain knowledge, you know that these two columns or these few columns will be interrelated one way or another, or because of high degree of correlation between multiple columns, then you can actually use I breakdown. But otherwise, you might want to use LIME or SHAP. And to decide whether you use LIME or SHAP, it really boils down to how much computational resources do you have? Or are you actually limited by computational resources? So it really depends on the size of your data in relation to your computational power, the processing speed of your computer itself. So if it's limited, it takes a long time, then maybe you want to use LIME because it generates its explanations much faster. But if you're unconstrained by your computational resources, you can actually use SHAP. So we hope this framework or this decision tree over here helps you understand which to use in what kind of situation. So there are actually some limitations to using row-wise analysis. And I'm going to establish what this limitation is by asking you guys this question. So how does attribute 24 affect my dependent variable? And the dependent variable in my case would be the probability of bankruptcy. How does attribute 24 affect the probability of bankruptcy? So you can take this SHAP plot that we have over here and maybe think of an answer. Okay, so for those of you who are sharp enough, you have seen this line attribute 24 over here. And you will notice that it actually increases the log odds of bankruptcy by 0.75. Okay, so this is great. But what if I change my question slightly? So what if the value of attribute 24 isn't 0.046 anymore? What if it's a bigger number like 4, maybe 5? Or if it's a much smaller number like 0.001? How will attribute 24 affect the probability of bankruptcy? Will it cause it to be much bigger or much smaller? Or will it cause it to contribute towards or away from bankruptcy? Think about it. Okay, the truth is, right, using these plots, these SHAP plots, line plots, or even I breakdown plots, you wouldn't be able to answer that question. Even if I gave you 2 or 3 of these plots, you wouldn't be able to answer that question. Because the answer to that question as to how this attribute 24 affects the probability of bankruptcy as its own value varies actually lies in what we call column-wise analysis. And we're going to do column-wise analysis through partial dependence plots. So by doing that, PDP helps to give us, PDP in the sense is what we call partial dependence plots, it's the short form for partial dependence plots. It actually builds a general intuition as to how any column of interest, basically any column of your data frame, affects the dependent variable. Okay, so now I'm going to go through a rough explanation of how this entire algorithm of partial dependence plots works for you to appreciate this concept a bit better. Okay, so just to make sure that we're all on the same page, now we have really come to the last step, which is column-wise analysis. So this is probably reaching the end of the entire presentation already. Okay, so let's start off with a very simple example. So let's assume we had a data frame on housing price prediction that had multiple columns A, B, C, as well as a Y column. Then it will probably look something like this. My column of interest is A, and I want to understand how A affects Y, which means how does my size of a house affect the price of my house? So for column A, I have 3 unique values for sizes, which is basically 1,000 square feet, 2,000 square feet, as well as 3,000 square feet. At the same time, we have other columns, B and C, and there are 3 unique combinations of values as well. So the unique combination would be 0.5 kilometers to the MRT, together with 15 years of age, as well as 1 kilometer to the MRT with 5 years of age. And the last combination is 2 kilometers to the MRT with 10 years of age. So now the PDP will take place in 3 steps. First, you'll identify the number of possible combinations. N combinations would be the number of unique values in the column of interest, which in our case is column A, times the number of unique combinations in all other non-target columns, otherwise known as non-Y columns. So earlier we saw that column of interest, column A, has 3 unique values. And your other columns, B and C, have also 3 unique combinations. So in total, 3 times 3, we get 9. So first we'll duplicate our column A 3 times. So 1,000, 1,000, 1,000, 2,000 all the way, and 3,000 all the way. Then what we'll do is we'll assign the unique values, unique combinations of B and C to the other unique values of column A. So originally 2 kilometers to the MRT and 10 years of age was assigned to 1,000 square feet. So now we will assign it to 2,000 square feet as well as 3,000 square feet. Similarly, 2,000 square feet originally had a value of 0.5 kilometers to the MRT and 15 years of age. We will assign that combination to 1,000 square feet as well as 3,000 square feet. And we will get something like this, this data frame that you see over here. But now we are missing the Y value for the newly created rows. So in the next step, step 2, we will use the underlying machine learning model that we pass in as an input to predict possible values of Y. So this is an example of what are the possible values that could be predicted. So if a 1,000 square feet house, it's closer to the MRT, when you compare basically rows 1 and 3, if it's closer to the MRT and much younger, 5 years of age instead of being 10 years of age, chances are it's going to be a lot more expensive, right? So this is what the model will probably predict as its price. So in step 3, which is the last step, what we'll do is that we will average out all the values of Y for each unique value of A. So what will happen is that you end up getting a table like this. When you add 1 plus 0.5 plus 2 and you divide by 3, you get this value. You do the same for 2,000 square feet as well as 3,000 square feet. Your resulting final data frame will look like this. So now we have a general intuition that when you increase the size of your house from 1,000 to 2,000 to 3,000 square feet, the value or the price of your house actually increases as well from 1.17 to 1.25 to 1.52. So I know that this is very intuitive because it's a housing price data set. However, for many other columns of your data frame, it's not as intuitive. So that's where partial dependence plots comes in. It helps us to better understand what the relationship is between any column of interest as well as your the relationship between any column of interest as well as your Y column. And PDP actually helps to negate the effects of all other columns of the Y value. So in our case, it helps to negate the effect of columns B and column C on the Y value. So let me show you how this happens by taking another example. So let's say I go back to the same data frame and I highlighted 3 rows in blue. So let's say the original value that was attached to 1,000 square feet was 1 kilometer and 5 years of age, and the price was $2. And for 2,000 square feet, it was 2 kilometers, 10 years of age, $1.25. 3,000 square feet, it was 0.5 kilometers, 15 years of age, and $1.50. If I were to plot a scatter plot using these rows, right, I'll end up getting something like this. So when you look at this scatter plot itself, does it actually give you the same general trend that the partial dependence plot gave earlier? It doesn't, right? Because in partial dependence plot, it gave us the correct relationship, which was that as your size of house increases, your price of the house also increases. But over here, what we notice is that as the size of your house increases, your price can actually drop. And in fact, the smallest house has the highest price. So sometimes doing a scatter plot itself, it's not going to give you the correct relationship, which is why we kind of need to use partial dependence plots. So I hope this explanation helps you understand the importance of partial dependence plot in establishing relationships between 2 columns. So let's take a look at partial dependence plots in our Colab itself. I'll scroll down a little bit and explain to you the code. Just a brief explanation. So basically what I'm doing here is that I'm extracting the columns that I wish to plot a partial dependence plot for. You can do it for every single column, but it's going to take a lot of time and computational resources. So if you're limited, what you can do is just plot the partial dependence plots for the columns that you find to be important. So to decide which columns are important and which will give you a very good indication of the relationships, what you can do is to go back to your feature importance plot and then decide, hey, I want attribute 24 because it's very important. Attribute 11 seems important as well. same as 5, same for attribute 5. And then you come down and then you just plot the PDP for those particular columns itself. What I'm doing next over here is that I'm running a for loop. So I'm going through each of these features. And what I'll do is I'll calculate a Z-score and then just eliminate the outliers to some degree. Because if I don't do this, what's going to happen is that the plots that I got were actually very, very narrow. When they are so squeezed in and narrow, I couldn't study the relationship properly. So by removing it, the plot expands a bit more, and then you can actually see the relationship a little better. And what you have over here, this is the stock code for actually creating a PDP plot itself. And for plotting it, it will be the next line of code. So this creates and this plots it. It's very standard code that you can actually find online as well. So I won't be going through how exactly to include all the parameters, but I'll show you how to study any one of these plots that we have gotten over here. So let's go back to the presentation slide where I have a PDP plot for attribute 46. So basically what this plot tells you is that as the attribute 46 increases from 0 to 1, the probability of bankruptcy actually decreases from 0 to 0.27. Beyond 1, the probability of bankruptcy does not decrease any further. It stays at 0.27. So using this knowledge, I hope that you can apply it to the other partial dependence plots that we got in our Colab notebook over here for attributes 11 or even attributes 24. All right, so it's pretty standard. So basically, just to summarize everything that we have gone through today, in order for you to unbox a black box model, there are 2 things that you need to do. One is to conduct row-wise analysis, and you can use line, SHAP, breakdown. You can refer to our decision tree flowchart to decide which of these libraries you should be using. And the next step is to do column-wise analysis using partial dependence plots, as you can see on this diagram over here. That's it for today. Here are references that we use to actually make these slides. And with that, we've come to the end of the presentation. Thank you so much for your time. This is our Q&A segment. We have about 9 minutes left. For more information, you can actually refer to our GitHub repository as well. We will be publishing a Medium article in due course, and we will probably attach the link somewhere to this GitHub repository as well. So just take note of this GitHub link. All right, I think we can begin our Q&A segment.
Yeah, okay. Yeah, so thank you all for attending today. I hope it was an insightful session, and I hope that it helped you learn more about explainable AI, what it's all about, and how you can actually implement explainable AI in your own models. Yeah, if you have any questions, just feel free to ask in the Q&A segment, in the Q&A function on Zoom. Okay, I think most of the questions here were currently asking whether you have access to today's presentation in terms of like a recording, right? Yeah, so we will be sharing the recording. It will be uploaded on the NUS Fintech Society's YouTube page. So if you would like to review what you have learned today, feel free to visit that page in probably a few weeks' time. Yeah, you should have a copy uploaded of today's session. Yeah, so other than that, thank you so much for attending today. If you have no questions, then this will be the end of our session, our workshop today. But otherwise, yeah, feel free to get your questions in. Yeah, and if you would like to know more about the FinTech Society, feel free to reach out to us on LinkedIn. Yeah, or if you want to know anything about like NUS, or I know we do have a few pre-university students here. So if you want to know more about NUS or our FinTech Society and how it works, yeah, feel free to reach out to us on LinkedIn. You can just search out our names there and connect with us. Yeah, otherwise, thank you so much for attending today.
Thank you. If you have any questions, you can just stay back and type it in the Q&A portal, and then we try and answer it as soon as we can. Okay, we have two questions. Hi, not related to the workshop, but okay, I have a question here that's asking about recruitment for FinTech Society this semester. Okay, we're not actually from the HR side, so we don't particularly know the answer to this question. I think what you can do is, if you do have Instagram, you can go to, let me check out their
It's NUS Fintech. Is it?
NUS
At
Fintech.
NUS Fintech.
NUS Fintech, yeah, it's just NUS Fintech, FINTECH. You can just DM them and ask them if there's any recruitment upcoming, and then they will hopefully be able to give you a better answer.
Okay, we do have a interesting question. All right. The question says, I heard that, okay, I answer live. I heard that studying computer science or data science needs, you need to be strong in math to do that. So what's the difference between computational math and like normal math? Well, I would say that, if you are in aiming at, if you are looking at NUS, the CS program here, we do have, most of the modules that we will be taking are computer science modules, but you do have some compulsory mathematics modules that you usually take in your first 2 years. Yeah, you should complete it by your second year, all the mathematics and stats modules. So these can be like linear algebra, these can be calculus, which is probably almost what you have done like in your pre-university, and also statistics, which is also pretty much like H2 math if you are taking the A-level system. Yeah, so there are definitely some overlap in terms of the mathematics, but what I would say is that in computer science, you're sort of implementing the mathematics that you learn, right? So there's like a running joke that computer science is applied math. Yeah, so it's not entirely false. You need to have some mathematical concepts, and then you're trying to apply them in code. And yeah, in a sense that you can achieve much more with code than you can by manually like doing math, right? Because you can make the machines run complex equations and algorithms in like as like you can run as many algorithms that you want using the computational resources that you have, right? As opposed to math where you're limited by one person writing on a pen and paper in most cases. Yeah, so yeah, there is indeed some overlap, but computer science is sort of an extension of it, and that's why in some universities you see computer science more in the engineering faculty rather than the science faculty, because there's a lot of application to this field, right? So yeah, if I hope that answers your question. It's pretty much there's an overlap, but computer science is a bit more applied than just regular math. Right, yeah, so do keep the questions coming if you have any. We have like 2 more minutes left. It can be like related to the the content just now, or it can be like anything that you want to know about FinTech Society or NUS or computer science. Yeah, otherwise we'll be ending, I think we have like 1 minute left, so we'll be ending the session in about a minute's time. Yeah, again, thanks so much for attending the session. Yeah.
Yep, any more last minute questions? If you do, just say, give me a minute, then we'll just wait for your question. Otherwise, we'll be ending it very, very soon. Okay. I'll count down from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, thank you so much, guys, for coming once again.
Okay,
And yeah, do
thanks.
look out for our video on YouTube itself. And yeah, you can watch a recording if you need to relook into this content as well. Yeah, thank you so much. Bye-bye.